All right, so now we start a new module, and I want to say that. So I read the agenda, right? So I think I have a high level understanding of what also our friends from SoftServe will cover in this week and also next week, and I think you will get a much deeper introduction into the individual algorithms, candidate algorithms for potential quantum applications delivered by them, right? So what I want to do is now just take a real life hybrid variational algorithm and again show you how you can run that on Braket and what may be the things you should pay attention to. So information may be doubled now, and I apologize for that, but it's just that I want to come up with a real life example because I think that that gives a bit of a better learning experience when it comes to things that need to be covered in Braket Hybrid jobs. So the context of this session is well, since we have learned how to run hybrid jobs in principle with using an admittedly super trivial example, so we wouldn't actually we wouldn't have needed hybrid jobs for that. So I want to now change that, right, and really look into, as I just said, into a real actual hybrid algorithm. And the algorithm we look at is called QAOA, and we use it to solve a paradigmatic combinatorial optimization problem, which is called maximum cut or max cut in short. And again, I spent just a few slides to introduce max cut and QAOA, but I will rely on SoftServe to give a much deeper, much richer introduction in the course of this bootcamp. Good. QAOA is an acronym for Quantum Approximate Optimization Algorithm, and QAOA is a very well-known heuristic to find approximate solutions, hence the name, to combinatorial optimization problems or a specific form of combinatorial optimization problems. And QAOA is designed to be executed on gate-based quantum computers. Now, let's review the very high-level overall structure, or let's say the flow of this algorithm. We have two main components, I would say, and the first ingredient is a quantum circuit, right? A parameterized quantum circuit. The qubits are initialized in some starting state, which is, so the starting state we choose is relevant for the actual problem we want to solve at. I will share some more information on top of that for that later on. And then we have a circuit which consists of two groups of gates. Let's look at that in a very abstract way at this stage. So these two groups, we call them UC and UM. And these group of gates, so two groups of gates, are repeated or can be repeated several times sequentially in that circuit. And these number of repetitions, or we say number of layers, is a hyperparameter to this algorithm. So the first group of gates, UC, is actually related to a cost objective, which mathematically describes the optimization problem we want to solve. And the entire circuit, so all the P layers, are parameterized with in total 2P free classical parameters. Typically, these two sets of parameters are denoted beta and gamma. So we have P, so a vector of length P. So beta is a vector of length P, and gamma is a vector of length P. Right. So then a single quantum task Well, consists of a series of circuit measurements, as you know already, so the number of shots, and we have to choose the number of shots in a way that we can sample the expectation value of the cost operator, right, or the cost observable. And that is the result of the measurement in QAOA, the quantum measurement, and we feed that into a cost function and we minimize this cost function. And I'm going to say a bit more about the details behind that on the next couple of slides. So second component in this algorithm is a classical component. So we have a classical optimization loop. So the circuit is executed multiple times iteratively with updated parameters until we find the optimal value, which minimize the cost function, right? So the cost function is minimized by the classical optimizer. So that's the overall flow. So I think I need to give you a bit more details to that, but let's first recall what is the scope of this talk. I mean, we want to we're going to use QA to solve the max cut problem. So it may make sense to also introduce the max cut problem. So this is a well-known NP-hard combinatorial optimization problem, which formulates in principle the following challenge. Given we have a graph with a set of vertices and a set of edges. So let's, for example, take this graph depicted here, consisting of 5 vertices and 6 edges. So then the max cut problem formulates the challenge of, simply speaking, seeking a partition, or we seek to partition the vertices into 2 complementary sets, which is now here indicated by the different colors, in a way that the number of edges connecting vertices with different colors is maximized, right? So for that color configuration, we have actually 1, 2, 3, 4, 5 edges. Edges on the cut, right? So, and that is one solution to the max cut problem for that specific graph. Good. Now, how can we, well, formulate that problem mathematically? Well, we can do this in the following way. First, we assign to each vertex a value, called a value Si, which can be either +1 or -1. And then we can sum over the edges, or yeah, let's say we sum over the pairs of vertices which are connected by an edge. And we sum up the term 1 minus Si Sj. And this is actually then our cost objective, okay? And we can verify that if the 2 vertices connected by an edge have the same color, they have the same sign or the same value of Si, then the contribution to the objective is 0. And if both vertices, or the 2 vertices, have different colors, different values, then the contribution to the objective is 1. Right? I mean that the 1 minus SISJ is 2, but we have here this factor 1 over 2. Well, before the sum, right? So therefore, the objective is 1. So this means we can actually solve this problem by maximizing this cost objective, or we can also, well, usually by convention, we minimize the negative. And this we can actually feed into a classical solver, right? And I mean, there are classical solvers out there. In order to solve these problems. So that's basically the way to go. Now, how we can now solve this on a quantum computer? Well, the task, I mean, in principle, we have to address 2 challenges when we want to solve this on a quantum computer. The first challenge we have is we need to map the formulation onto or we need to translate this formulation into an equivalent Hamiltonian, so into something a quantum computer can process. And what we see here is the default quantum embedding for the max-cut problem you can find in the literature. We have here a Hamiltonian, which is again the sum over the edges. And what is done here is we have mapped these binary, I mean, it's not binary, but the values Si onto the eigenvalues of the Pauli set observable, right? So, and this works in a way that, so for each edge, right, the term in the sum has a non-zero eigenvalue only if the vertices have different set value measurements. So, and with that so-called cost Hamiltonian, the optimal solution to this max-cut problem corresponds to the ground state of the Hamiltonian. So that means we have now translated the max-cut problem into finding the ground state of this Hamiltonian, right? Great, so this can be done with a quantum computer. However, generically, it's really hard to find the ground state of such a Hamiltonian, because a generic Hamiltonian can have whatever complex energy spectrum, and it's a priori not, I mean, it's not at all trivial to find the ground state in a Hamiltonian, not with quantum computers. So what I want to say here is it's important to understand that solving this problem is hard classically, but is equally hard on a quantum computer to solve it analytically. So what we, however, can do is we can use QAOA to approximate the ground state, right? So QAOA does not give us an exact solution. It gives us an approximate solution, similarly to the classical solvers that are out there. Now, let me take a sip. I have mentioned the term Hamiltonian a lot of time, and I acknowledge that this may be well known in the audience, but maybe I should give a bit of background information about Hamiltonian specifically for QAOA. So I just spent one slide here for the curious in the audience. These two groups of gates I have mentioned, UC and UM, they are not equal to Hamiltonians, but they directly correspond to Hamiltonians. And UC in the circuit diagram corresponds to the cost Hamiltonian, which we have just formulated on a previous slide. And UM corresponds to what is called the mixer Hamiltonian. At a very high level, you can think of the mixer Hamiltonian as a term which is needed to prevent the algorithm from getting stuck in a specific trial state. So in the optimization loop. But in addition to that, there are some very interesting resources in literature that you can use the mixer Hamiltonian to also constrain the accessible subspace of the solution, meaning that you can, when you tune the mixer Hamiltonian, you can make your algorithm also more performant. And two resources I want to share with you in these regards are given here. So I mean, this is a good learning material I can highly recommend. Specifically, the left one here is no, the right one. Sorry, is giving you a selection of different mixer and also cost Hamiltonians for different optimization problems. So it's a quite interesting repository. Okay, what else? All right. So for the curious folks. Can you post the archive in the chat? Well, I can. Let me. Well, I would maybe just type this off. and then you can feed this into Google or your favorite search engine, and that I don't have the links available right now. No, thanks, Christopher. Excellent. Cool. Thanks for your help. Alrighty, so where was I? Okay. Now, for the curious folks in the audience who still want to know exactly how these UC and UM correspond exactly to the Hamiltonians, well, take a look at this box here. What you find here, first of all, is the Schrödinger equation, right, which describes the time evolution of a closed quantum system. And this, so in the first line of this box here, and the Schrödinger equation contains the Hamiltonian, and the Hamiltonian in that picture, you can think of it. It describes the energy landscape of the quantum system. Now, the solution of this differential equation here in the second line, here you already see this exponentiated Hamiltonian, and this exponentiated Hamiltonian corresponds to a unitary operator. And in gate-based quantum computing, these unitary operators represent our quantum gates. So in principle, this exponentiated Hamiltonian can be seen as a pseudo gate on a quantum computer. And this is exactly the UC and the UM we have up there. So these are pseudo gates that represent the Hamiltonian. So I said previously that we have to solve we have to address two challenges when we want to execute that on a quantum computer. So then the second challenge would be to find a gate decomposition for these pseudo gates, right? So find a decomposition into operations which can be executed on a quantum computer. And I want to show you this on, I think on the next slide, and also the next slide. So we have the Hamiltonian. We want to get the ground state of this Hamiltonian, and we use QAOA to approximate the ground state of this Hamiltonian. And QAOA works in a way by preparing this parametrized ansatz, which is which is given here, and then use a classical optimizer to update the parameters to approximate the ground state. Now, QA's wave function is parameterized with these two sets of parameters. I think I mentioned already, beta and gamma. And for the max cut problem, what we use here is we use a single qubit Rx rotations as for the mixing term. And we use 2 qubit ZZ unitaries for these spin-spin interactions that are described in the cost Hamiltonian. So these are the standard gates that are used for the max cut problem. And also, as I mentioned earlier on, the starting state is relevant for the performance of the algorithm. So for the max cut problem, we start with a uniform superposition of the computational basis states. Good. If this is too abstract, then let's just look at the diagram. This is much easier, right? So here this is an example now for this problem we want to solve for the QA circuit for the max cut problem. 2 qubits, meaning like a 2 vertex graph, and 2 layers. And as you can see here, we have 4 free parameters. Exactly. So gamma 1, gamma 2, beta 1, beta 2. And so finally, what we then do is we measure the expectation value of the cost Hamiltonian, right? So this is basically then our cost function, which we minimize. And therefore, we find the ground state of the, we attempt to approximate the ground state of the cost Hamiltonian. And we are done. Great. Time to go back to the note. Oh, well, yeah, I want to add I want to add one more sentence on the layers, right? So in principle, QAOA can reach the global optimum of the cost function, right? And but typically, so this can be reached in the limit of large P, right? So because if you increase the number of P, then you kind of approach the adiabatic protocol. I don't know if that maybe goes a bit too deep, and maybe my software colleagues will cover that in more detail. So in principle, so what I want to say is, you typically make the results more accurate when you increase P, the number of layers. But this comes with a cost, and that is circuit depth, right? Because you have a deeper circuit, you have more gate operations. And today, with noisy quantum devices, this can also make, or will also make your result of your computation worse, because the more gates, the more gate operations you have on a quantum circuit, the more affected is your computation by the noise of the devices. So this is just to keep in mind. Anyways, let's now go to the notebook again. So what do I need? I need to, yeah, this should be it. Okay, cool. So we are here again on the landing page of the workshop studio material. And just because I received a question early on, or I think during the break, so the question was, where do we find these materials? So when you are logged in to the workshop studio environment and you find these modules there, you can download them. But they are also, I mean, for you to make it convenient to explore them, they are already deployed into the notebook instances. So we now look at MaxCut with QAOA on hybrid chops. So this is what we're going to do now. I go back to the Braket console. I go back to my notebook instance and go to the directory Braket workshops, immersion days, QAOA, MaxCut, PennyLane, hybrid chops. In here, you find a notebook, you find a Python script, and you find an image directory. So let's open the notebook, and I keep now the file browser open because I will use it later on. Okay, so this notebook again comes with a lot of text, right? So we're gonna skip all the text because I think I mentioned all that in my slides. But just to call out, this notebook actually builds on, so these are links here, right? So this is a link and this is a link. So this builds upon a Braket example notebook called Using PennyLane with Braket Hybrid with Braket chops. So we are using now PennyLane for the implementation of QAOA. But we also have a notebook I quite like, actually. So it's called Braket, and it's called QAOA Braket. And that gives a lot of details. So let's maybe click on it. So that gives a lot of foundational details about QAOA, hybrid algorithms, but also the MaxCut problem and actually how you can code it up. So this is a very good reading material created by my colleagues. So this is definitely a good place to start for if you want to delve a bit deeper into QAOA and how you can also code it up yourself, for example, with Braket SDK primitives. But for the sake of this tutorial, I think I've got 30 minutes left. Yeah, I'm doing quite good on time, that works. So let's walk through this notebook here. So yeah, we already know what QAOA is, how it works. So let's start with an example graph. And obviously I picked just the same graph I showed you already on the slides. So we have here a 5 vertex graph with 6 edges. We're using some graph library to create this graph. So that doesn't matter too much, to be honest, but what we then need to do is we need to sort of serialize this graph object, right? Because the graph serves as an input to QAA, and we want to run that on hybrid jobs, so we kind of need to upload that to the cloud. So this is what we do here in that cell. There are 2 ways. So we are using this NetworkX library here, which has several ways to serialize a graph. We are using here this adjacency list because you use the edge list or whatever. This really doesn't matter, right? So all you need is a serialization of that graph. And by executing this cell, we have this now here, the graph dot edge list here on the file browser, locally in our development environment. I will go through the QAA algorithm implementation once the hybrid job is running. So let's, for the moment, just take this algorithm implementation we have as a black box. What we first do is the local execution, right? So this notebook is our development environment. We have the algorithm code here, which is in the maxcut QAA.py file. We have the input data, which is the graph.edge list. And then we are using, so this notebook comes pre-installed with the Braket SDK and with PennyLane, all good. And we use these classical compute resources of the notebook to both execute the quantum and the classical part of this algorithm, right? So this is what we're going to do now. So we just load the Python modules from this file. We instantiate a device. In that case, we are instantiating a local local PennyLane Lightning simulator. And then we execute the function run QAA, which is here in this maxcut function. We do this for, I should first start it. We do this for p equals 1, so for just 1 layer and just 10 iterations. We are printing the cost Hamiltonian. So these are the spin-spin interactions using the set operator or set gates then. And we use the RX gates for corresponding to the mixer Hamiltonian. Starting with some initial parameters, and then we have here our iteration again. In every iteration, we evaluate the cost function, which is the value of the cost function is here. And we're going to log this. And then we are done with our optimization, and we return the optimized parameters for our gates, for our parameterized gates. So in principle, what's the result of that execution is the exact realization of the circuit, right? Good. So let's execute this as a hybrid job, and we are doing just the same as we have done in the previous example. The only tweak or the only difference is that we are now using an embedded simulator. So a simulator running on the jobs container instead of a high-performance simulator. Why? Because of 2 reasons. First of all, we will execute a circuit with just 5 qubits. So you can really simulate that locally very efficiently. And second, as we will see, we will use quite a large number of tasks, which we're going to discuss a bit later on. Okay, so what we need to do, we again need to write our wrapper function, which I now call QAA maxcut PennyLane. This is decorated with the hybrid jobs decorator. Compared to the previous example, we now have to use some more arguments here. So we have input data we want to upload to the cloud, and that is the graph, the serialized graph. So this we can do with input data equals, and then the file path. right? So with this line here, we are uploading the graph when we create the job. We need to do that. And then second, because we have here an external module we use as, or where we have coded up our algorithm, we need to include this module as well. So we need to upload the code as well. And this is done with this include modules instruction. So this can take a single argument, single module, or it can take a list if you have more. All right, so then here is our wrapper function, which prepares the input data for the algorithm. So in principle, here we execute the algorithm. So this is the function we executed also locally. But because this function is executed on the cloud, we need to prepare the input graph and the device. Okay, so in the input graph here, so we just read the input graph from the file we have uploaded and create the graph instance, right? This is what we do here. And the device we create based on, so this is a helper function provided by Hybrid Jobs based on the device arm we are passing in here. Okay. So this is basically the boilerplate code for preparing the inputs to the function. Here we execute our algorithm. And here we save the results to our, well, we save the results of the algorithm as results as job results. So they are so that data structure is stored on S3. So sometimes you want to store also other things than just a plain Python dictionary. You want to have kind of some control graphs. You want to have, I don't know, whatever. This you can also do by just storing any kind of files into a specific directory on the jobs instance, and that is going to be then packaged. So that's going to be zipped and tarred into a tarball and also stored as part of the job results, right? So in principle, you can store whatever results you want to store as job results. Good. Oh, I made a mistake. I should have executed that. All right, anyways. All right, so now let's execute the job. Job is running, job is queued. That's great. So now that gives us a bit of time to look into the algorithm code, into the implementation. So we are executing this function run QA, right? So what do we have here? In this example, we are using from PennyLane, we are using the module QA, which gives us reference implementations for graph optimization problems. For Hamiltonians, QA Hamiltonians for specific graph optimization problems. This is really quite convenient. So let me. Here's the documentation. I should maybe add that link also to the notebook, but let me just share this with you on the group chat. So as you can see here, you can select some generic Hamiltonians. You can come up with your own Hamiltonians, but you find for some well-known optimization problems, you find reference implementations like for the max click problem, maximum independent set, or here the max cut problem, right? So you find here the standard Hamiltonians. So that's maybe also a good link to share. So if you want to learn a bit more about how PennyLane implements these Hamiltonians, then have a look into this resource. So here we get the cost in a mixer Hamiltonian. For max cut, QA for our specific graph, right? We want to solve the problem for. Then the next thing we want to do is we need to code up a QA layer, and the QA layer takes the two sets of parameters, right? So a vector gamma and a vector beta, or an array, and each layer consists of the execution of a cost and a mixing layer. And this is also quite nice. So cost layer takes a Hamiltonian, so that actually transforms the Hamiltonian into unitary. Quite convenient. We don't have to code that up on our own. Awesome. And then finally, here's our circuit consisting of two elements. First, we apply a series of Adamar gates for state preparation. As I said, we start with a uniform superposition of basis states, and then here we have p times a QAOA layer, right? So here we address the hyperparameter p. We add the QAOA blocks p times. Finally, we just evaluate the expectation value of the cost Hamiltonian, and this is basically our cost function. Great. So then all we need to do is instantiate an optimizer, a classical optimizer, and start our optimization loop. So here we don't have any kind of convergence criterion. We just loop over a fixed number of iterations. We evaluate the cost function in each step and update the parameters. And again, we just log this cost metric. And then finally, we store the optimized, so we get back the optimized parameters, and we store the optimized parameters. Now here we have a piece of code which I added here to verify the results of our optimization. I want to skip this for now, but come back to that part later on. Great, so let's now see how we're doing with the job. Again, completed. So I talked long enough. That's good. So let's look into it and just maybe monitor. Let's just look at the log cost function. So you can see, yeah, this is what the optimizer came up with. Here you already see, I mean, this is now a real life cost function. The optimization performance of the algorithm can definitely be tuned, right? So tune, for example, the step size for the optimizer. You can tune the number of iterations, obviously, right? So all that, well, is then a task for an algorithm developer. So you can do hyperparameter scans essentially in order to tune the performance of the algorithm. But this is now what we have achieved in our execution. So let's go back to our notebook, verify the job state. Here we just, yeah, so, well, this cell, I should have executed that cell once when the job was still running, but anyways, we just programmatically can retrieve hyperparameters, information about the job, obviously. Now, because the job is completed, we can download the job results. So in this case, two things happen. First of all, job_results is now the Python object or the dictionary of, so it's the same data structure that we return here, right? Well, the same data structure as we return here in the return statement of our wrapper function. But in addition to that, you also see that we now have here a tarball on our file system. So this got downloaded together with our job results. And if we look into this tarball, then we see we have a results.json file, and that's exactly the data structure of our job results. This is the JSON file that is stored on S3. So this is the persisted data structure. And we have a graph.png, right? So that's the file we stored in our wrapper function. So, and this is just an example that you can store whatever you like as a job result. Okay, great. Let's inspect now what we actually, I mean, what resources we consumed. So you can see here that we didn't spend a single dollar for a quantum task. The reason for that, we used an embedded simulator, right? So we used the simulator on the job instance. The job instance ran for about 1 minute and 20 seconds. So now let's investigate the results. And now the question is in QA, what do we do with our optimized parameters, right? So we now actually have, we get our 2p optimized parameters. I mean, how does that solve the max cut problem? Well, under real life conditions, this is a different story and maybe a more lengthy discussions. But in the books, what you can do, what you usually do, is you instantiate the circuit once again with these optimized parameters, and then you just sample many shots. So you execute this fixed circuit, this optimized circuit with many shots, and you basically sample, you measure all the computational basis states you observe, and you sample the probabilities for measuring these basis states. And this is exactly what I was skipping before, right? So here we do that. So we create another circuit where we where we use the optimized parameters. So here, and then we just sample the probabilities for measuring each of the basis states. And this is also returned as a job result. So when we look into this, what's the result? That's the result. Okay, so what does it mean? So we see here on the x-axis all the possible bit strings we can measure or we observe when we do computational basis measurements of all the qubits. Right, so we have a 5 vertex graph. That means we have 5 qubits, and these are all the different bit strings we have measured. What we also see is that 4 bit strings kind of stick out here. Okay, so it's, for example, the bit string 00011. It's the bit string 01100, and 2 more. Let's look into these. So let's now draw the graph once again, but let's color the vertices. So if we measure a zero, a value of 0 in the computational basis, we color it blue, and if we measure a 1, we color it red, for example, or vice versa. I don't know. So when we now take the 5 most probable outcomes here in this histogram, so that is these 4 high bins and then 1 in addition, then what do we see? I mean, the most likely outcome has this graph configuration, and you see that indeed this is a solution to the max cut problem of that graph. Excellent. So the next 2 highest probable result looks like that. And if we look at it, it's also a valid solution to the max cut problem. Similarly as the third, yeah, this also has a value of 5. And also the fourth. So recapping, the 4 highest bins here all correspond to equivalent solutions to the max cut problem. We have a graph which does not have just one unique solution to the max cut problem, but which has 4. So yeah, fair enough. So what is then with the 5th most probable result? This is that graph here, and this does not result. I mean, this is not corresponding to a maximum cut. So what's the takeaway here? Well, the good thing is that we have learned that in principle, by executing this algorithm, we get all the solutions to the max cut problem, which is great. The downside to, the downside to this is we have to do some post-processing. some classical post-processing, right? So we need to look into the results. We need to analyze the results in order to verify what are the maximum, the solutions to maxcut or not, right? So this is how it works. Now, here's the call out. So you have these AWS environments for another 1.5 days, I think. So I invite you to play around with this notebook and tune the hyperparameters. I mean, change the number of iterations, change the step size, change the layers, and observe how that histogram will change. So what you will observe is that the better you tune your QAOA algorithm for that problem here, the more prominent the actual solutions to the maxcut problem will be in this histogram, right? So this is the homework, if you like. So if you're interested, then you can explore that. And this is now, I mean, and this now really has joke aside, this really has a real life. This is corresponding to the real life tasks of quantum algorithm development, right? So in particular with these hybrid or variational algorithms, which are purely heuristic, they need to be tuned for every problem at hand. And that actually makes tools like Braket Hybrid jobs more valuable, because it's not just like you're doing one final run to evaluate your results and then write your paper, right? It's really, you have to scan over your hyperparameters. You have to optimize these conditions of your algorithms in order to find the best possible solution. There is a question on the chat. What modifications to the hybrid job are necessary to run it somewhere other than in the online notebook? That's a good question. Okay. So in principle, so you can download the code, right? So this, so let's say you download this zip file here, right? Or the zip file here. And then in the zip file, you find this maxcut QA implementation and the notebook. So, and when you have somewhere a Python environment, you can install the Braket SDK locally, and you can run this locally in any environment you have. I mean, this is a notebook, so you can also just take all the code example, the code cells, and put it into a script and then execute that script, right? I want to share with you a blog post. So this blog post talks you through the steps you need to do to create or install a local development environment on which you can then execute locally your quantum tasks, but also your hybrid jobs. So this gives you the walkthrough to that. All right, you're getting an error, unsupported region. You may need to upgrade. Okay, well, unsupported region. So what you should, hang on, no, sorry, here. So there's one thing you need to keep in mind. Let's talk about Braket regions. So Amazon Braket is available in 4 regions currently only. It's Northern Virginia, Northern California, Oregon, and London. The reason for that is because the devices we currently have on Braket are located in these regions. So for your region, AP Southeast 2, Braket is not available. So therefore, you can't use Braket or Braket SDK on AWS session for Braket in that region. So in the notebook, this shouldn't be an issue because the notebook is running in US East 1. So where did you encounter that problem? I mean, did you install the notebook locally, and did you try to connect to the Southeast 2 region? So if you want to run if you want to run it completely locally, then you need to do two things. You need to first make sure you're using a local simulator, and then you would have to do local equals true. And then this is executing just locally. You're not even requiring, so you're requiring the Braket SDK, but you're not requiring an AWS account. Okay? L27. I don't have a cell 27 here. All right, Sharif, I don't have a cell 27, so, but I tried to answer the question how you run that offline. And again, I mean, I recommend to read through this blog post here, post the link once again, and that gives you hopefully more clarity about how to run that, how to run completely offline. Cool, excellent. What else? Okay, I think we've addressed these questions. Cool. Okay. So that's about it. I wanna close with one with this cell here. There is a note, and I recommend, so if you want to run the same code either on a Braket on demand simulator or on a real QPU, then read this cell carefully, because again, under real life conditions, there is a bit of validation work you should do before you run on a Braket backend, because when you run on a Braket backend, this will, charge you for the tasks you're executing. And so therefore, do a proper cost or resource estimation, right? So typically what you should do is run it with one iteration only, the algorithm, because then you can find out how many tasks your algorithm creates per iteration. Why does your task, so if you look into our task, we can see that, can we see that somewhere? Let me down here. There's a job result, I think. I did not log this, but I mean, typically, so a task. So in a hybrid algorithm, you normally have several tasks per iteration. Can somebody tell me why this is the case, or why this can be the case? Any ideas? The reason is because your algorithm code, sorry for scrolling around so wild. So when you make yeah, exactly. So one iteration of your loop has multiple calls to quantum divides. And the reason for that is that your optimizer usually has some kind of gradient estimation strategy it follows. And when you don't have available full differentiation of your cost function, then what these optimizers typically do, they do some kind of parameter shift techniques. That means depending on the number of free parameters in your cost function, they shift the parameter, evaluate the cost function again, shift the parameter, another parameter, evaluate the cost function again. So they do multiple evaluations of the cost function in order to estimate in which direction they should change the parameters in the next step. So, and every execution of the cost function will result into a quantum task. So therefore you can have tens, or in the worst case, I mean, normally not for QA, but I mean for kind of quantum machine learning circuits with a lot of free parameters, you can have tens to hundreds of tasks per iteration, right? And therefore you blow up your number of tasks, you end up with thousands of tasks in your hybrid jobs execution. And that obviously you need to estimate somehow. And because this algorithm is a heuristic, the best you can do is to evaluate this in a single iteration. And then you know, okay, one iteration of my algorithm, I will have to do 150 tasks, right? So do that. And the second is check, obviously, the supported gates on real quantum hardware, right? So you may have to come up with a kind of specific gate decomposition for your circuit to make it run on real quantum hardware. Okay, so that are the takeaway items I wanted to share. That's basically what I have covered. I'm running a bit over time, but I want to spend now maybe 2 more minutes to talk a little bit about other learning resources. I want to advertise here the Amazon Braket digital badge, and maybe Albert can share the link to the skill builder course. But here's also the QR code you can scan with your mobile phone. We released a free of charge learning resource last year, end of last year, around reInvent. So that gives you several hours of quantum computing courses. You can go through these on demand, no additional charges, and you can get this Braket badge in the end when you pass the final exam. So that's great to learn about Braket, also learn about Quantum Compute 101. Second resource, the Amazon Braket example notebooks I have already mentioned a couple of times. Here's the GitHub repository, great learning resource. Whenever we release a new feature on Braket, we also create an example notebook such that you can learn how you can use that feature. So I recommend you take a look into that. And then finally, if you want to stay in the know, we have our AWS Quantum blog channel where we blog about new releases. We blog about solutions we build, research collaborations we have with customers or public sector institutions. So that's also a great resource. And with that, I would like to thank you also on behalf of Brajesh, who was running the session yesterday. Apologies for running 5 minutes over time. Yeah, I would like to hand back maybe to Anne, but I'm also happy to stay a bit longer to answer a couple of questions. Thank you so much for your attendance.